Hello everyone. In this video, we discuss computation graphs and backpropagation in PyTorch. PyTorch is the most widely used machine learning / deep learning framework that allows us to train neural networks. And a big part of training neural networks is to first find the error through some loss function, and then we try to minimize the error by finding how to tweak the parameters. And in this process, we have to find partial derivatives or gradients of the loss function with respect to parameters. Later on, we're going to discuss this more within a neural network example, but in this video, we want to understand this from a very basic mathematical example. So let's say that I have a function that depends on multiple xi's. So for example, x1, x2, x3, if n equals 3 here. And therefore, this function here depends on all these three inputs. And in this case, it's a very simple function. So for each input, we add 2, we square that, we add 3, and then we take the average, right? So if you think of this term in front of the summation as just one function of xi, this means that we are taking the average or mean of those values. So obviously in this case, because it's very simple, we can solve this problem by hand and we can find these derivatives, or it's better to call here partial derivatives because we have more than one input of this y with respect to xi. And remember, here you have this summation, and summation is a linear operator, so you can find the partial derivatives of inside this summation. And there's only one term with the index xi, where I goes from 1 to n. So in this case, we get 1 over n as the constant, and then you have to find the partial derivative of this term with respect to xi. And remember that this plus 3, when you find this partial derivative, it's always 0, so it doesn't really change anything. So the main term that we have to find its partial derivative is this xi plus 2 squared. And this is simple because it's a quadratic function, which is 2 times what we have inside these parentheses, which is xi plus 2. So in this case, means that now if I put together all these partial derivatives, which then it forms something called gradient, which is basically a vector that has all the partial derivatives with respect to x1 to xn, then we get 2 over n, and then x plus 2, where this x now is a vector. So the ith element of this is xi. And we put together all these partial derivatives to find this gradient. And if I assume that my input x, in this case, has 3 elements, 0, 1, 2, then you put 1 times 0 here, then you get 2, and also n equals 3, so 2 over 3 times 2, which is 4 over 3, and then you add 1 plus 2 and 2 plus 2. So you get this gradient vector here analytically. So this is if we can actually do all these computations by hand. And if you have any questions about this, feel free to leave comments. But how does this work for PyTorch, right? So obviously PyTorch is not really solving this problem with the exact logic that we do here, because this is a little bit complicated and we may have a lot of parameters. So the way that AutoGrad, which is the sort of like implementation of this backpropagation in PyTorch works, it starts from local and then we go global. Meaning that in this case, if our input is x, we'll kind of like track how what operations we perform to get to the output. The first operation is we add 2, right? So, and I like to call this now a, as so like an intermediate step. Then whatever this a is, we are going to square that. So that would be a squared equals b. And then b will be added to 3, and that gives us c. And then y is technically the average or mean of all these c values. And this is exactly the idea behind that computation graph, right? So we had x, we added 2, this gives us a, so that's the first equation. Then we square this, then we add 3, and then we get to the output. However, remember, when you want to now find partial derivatives or gradients, you always want to go backward. So that's exactly where the term backward in PyTorch comes from, because now we want to go backward through this graph. And remember, in terms of like graph terminology, that's now our root node because we're going backwards. And this is our leaf node, right? Sort of like the leaf. And it would be easier if we rotate these 180 degrees, then it may make a little bit more sense how we get from root to leaf, but it is still clear if you follow these arrows. So this means that something like PyTorch, the way that we solve this problem, or PyTorch solves this problem, is that it starts doing this locally. And we're going to see that we first find partial derivative of b with respect to a, which is 2 times a, since it's a quadratic function, and then c with respect to b, and then y with respect to ci. And each of these terms are very simple because they're very basic operations. So that's the goal here, to go from complex operations to basic operations. And now obviously if you use the chain rule, then you're going to multiply these partial derivative of y with respect to ci, and then c with respect to b, b with respect to a, and that way you can also go from a to x, and this will give you the same formula that we had before, 2 over n times x plus 2. Well, how does this work in PyTorch? That's like the key question here. So in this case, to show this how this works, we start with importing PyTorch as torch, and then we're going to define this input vector x using torch.tensor. I have a video previously that explained how this works. This converts a Python list to a PyTorch tensor. But the main thing you have to do here is to set this requires grad equals true, because here we need to find the gradients of our output y with respect to x. So this is extremely important to set this equal to true, so that PyTorch knows that now has to follow all these operations performed on this x. And then in order to be able to build our computation graph, we need to tell the forward path, right? So if I reverse these arrows, right, like how we get from x to y, right? So in this case, we add 2, we get a, we raise a to the power of 2, add 3, and we take the average. And that gives us the output. Something which is very important, and this is one of the most important parts of this lecture, is that if you want to know the partial derivatives or gradients with respect to these intermediate variables, the PyTorch by default does not do that, because it's going to save a lot of memory and resources if we don't store them, because usually we just need to do this with respect to the leaf nodes. So if you really want to inspect those things for one reason or another, you need to use this retain underscore grad. So this means that retain gradients of these 3 intermediate variables a, b, c. And once you define these, so this is something that, again, you need to do this if you want to know these intermediate partial derivatives or gradients. And after this, you use this y that backward. So remember, when you say backward, it's exactly this idea here. We want to go backward and find these gradients. And the gradient of y with respect to x, or partial derivatives of y with respect to x, is stored in x.grad. Basically, it's an attribute of this tensor here. So in this case, we use y dot backward, so meaning that now we have our root node y, and now we see partial derivative of y with respect to y is 1, and then we can use that chain rule to go back. And now if I print the result, so you can see that in this case, where we had x to be 0, 1, 2, the value of y, the actual value, is 12.66. And usually this is not something we care about a lot, because we want to know how we can actually change this y by tweaking these for example, parameters like x. So what we really care about is this dy dx, or gradient of y with respect to x. And that's exactly what we expect, right? So remember, it's 2 over n, or 2 over 3 times x plus 2, right? And as we did the math here, so the result should be 4 over 3, 2, and 8 over 3. And this is exactly what we get here, right? So this is 4 over 3, and then 2, and then that we have here 8 over 3, which is very close to 3 if you notice that, right? Because if we had 9 over 3, we would get exactly 3. But the key thing here is that because we put this retain underscore grad on these intermediate variables, now we can actually find these gradients or partial derivatives with respect to intermediate variables, which is really interesting. Right, and let's start with here. So what's the partial derivatives of y with respect to c, right? So remember, this is kind of like this stage that we have. So y is simply average of c, and in this case we have 3 elements, so it's 1 over 3 c1 plus c2 plus c3. So this means that all these partial derivatives should be actually 1 over 3, which is this 0.333. Now we can find partial derivatives with respect to b. So in order to see this, we actually did the math here, right? So you find the partial derivatives with respect to ci's and then c with respect to b. So you have to multiply these two things. It still is 1 over n. And if you want to find the partial derivative with respect to a, so now you have 1 over n times 2 times a, right? And that's what we get here for these partial derivatives with respect to a. So to wrap up this video, remember when you use computation graph means that we keep track of operations on parameters that we have requires grad equals true. We form actually a graph. So now we have this root and leaf nodes. And backward, always we go backward in this computation graph. And the goal is to now be able to find these partial derivatives using simple operations. I hope you found this video helpful, and please don't forget to like and subscribe.